Okay, let's get started. Here we go. Okay, so we're starting to create these rules, kind of like shortcuts. They're shortcuts for finding rate of change functions really fast and in closed form really fast. Okay, so we already have 4 rules under our belt, right? The rate of change of a constant function is 0. The rate of change of a constant times another function, you hold on to the constant and it's times the rate of change of that function. And then the rate of change of the sum of functions, it's just what we like, right? It's like it's the most, the easiest result we could think of. It's just the sum of the rate of change functions. And then on Friday, we did the power rule, right? So x to the n, its rate of change is n x to the n minus 1. So x to the n, rate of change is, you can think of bringing that coefficient down in front to be bringing that power, that exponent down in front to be the coefficient, times x to the, and then you reduce the exponent by 1. And we saw, even if the exponent is negative, you don't take the exponent closer to 0, you truly, literally subtract 1 no matter what that exponent is. So if it's negative, it's going to become more negative. 1 more negative. Okay? All right, so let's look at another function here. The rate of change of square root function. Square root. Okay, that's one that comes up a lot. So if we want to figure out a rule for the rate of change of the square root function, how do we start? Where's Colton? Monday morning. Ready to go. Colton Lish. Is Colton here? Noted. Christian Masad. Where's Christian? Not here. Noted. Where's Sopuade? Yes. How do I start? I want to find the rate of change of this function f, the square root of x. What would I do first? No, but I know where you're going with that. We're going to talk about that later. I want to do it like I didn't know that rule. Like I didn't know the power rule. How would I start?
So that it would be the square root of x plus h minus square root of x over h.
Right, we're going to use our trusted form, right? Our rate of change, our general form of the rate of change function. Good job, okay? So our trusted form is going to be what? Let's just write it down here. If it's f of x, then our trusted form of the rate of change function is change in y for a change in h over change in x, which is h. We can always bank on this to be correct for the rate of change. And I'm going to show you how we can we're going to check answers using this later in class, okay? So, and then what is f? So then for this particular function, square root of x, she filled in the blanks, right? F of x plus h is square root of x plus h. F of x is square root of x over h. Okay, so we know this is right. So as we've seen before, we want to work on this to get rid of that h out of the denominator so that we can make h small, or like essentially 0, right? So we just have to remember from Algebra 2 that we have this formula. It's going to be helpful here. Do you remember this? A minus b times a plus b is a squared minus b squared. You have that middle term that becomes 0 because you have minus ba and plus ba, so the middle term of this is 0. So you're just left with a squared minus b squared. So we want to use that fact to help us here. It helps us get rid of the square roots. So you see, what do we have? Essentially, we have a minus b. So what could I multiply by to get rid of these square roots then? Yeah. And what would a plus b be in this case? Right, so now this is called the conjugate. The conjugate is where you have the same two terms, but then you have the opposite sign of the second term, and that would be like our a plus b, and then you see what we're going to get is this thing squared minus this thing squared, which takes off the square roots. See that? So we're just going to multiply but if we do it times the top, we got to do it times the bottom. We're going to multiply the top and bottom by the conjugate, or what would be like a plus b. And then in the top, that's going to result in a squared minus b squared, which means the square roots go away. You see that? And we're just left with x plus h minus x. So now I'm applying this rule right here. That's what the numerator becomes when you do a squared minus b squared. Square root of x plus h squared is just x plus h. And square root of x squared is just x. And so the numerator becomes simply h. And then again, that's nice because then h over h is 1, and then we got rid of the h in the denominator. So now we have, for h really, really small, this is essentially equal to 1 over square root of x plus square root of x, or 1 over 2 square root of x. So we just got another shortcut. We just got another shortcut rule. When you have the square root of a function, square root of x, its rate of change functions is 1 over 2 times the square root of x. And we showed it by doing all valid algebra from our trusted form. From our trusted form up there at the top. Okay, questions on that little derivation there? So the algebra is important, but the most important thing about this is if you want to find a rate of change function, you always start with the trusted form. The change in y for a change in h, right? F of x plus h minus f of x over h, our rate of change function. That's kind of the centerpiece of what we're doing here right now when we create all these shortcut rules. It's all about that trusted form of the rate of change function. Okay, questions on this? Okay, so but notice also, and this is where she was going, that square root of x is the same as what? X to the 1/2. So we kind of already knew what the rate of change of square root of x was because we could think of it in the perspective of x to the 1/2. So if it's x to the 1/2, then what would it be? Where's Jasmine? Yeah. So how can we knew what that was already? What's the rate of change of x to the 1/2? Right. So we can do the power rule, right? So we can do the power rule, which would be 1/2 x to the, and then we subtract 1 from the exponent. So it'd be 1/2 x to the minus 1/2. So it's still the rate of change function, so these two things should be the same, right? What we derived with the trusted form and what we just applied with the power rule, they ought to agree because it's going to be the same rate of change function if we started with the same function. So do they agree? What is x to the negative 1/2? Right, so the negative exponent means 1/2 in the denominator, and x to the 1/2 is square root. So check, the power rule confirmed what we derived, right? The power rule confirmed what we derived. Okay, so let's talk about how we can check these with GC, okay? Because our algebra is prone to mistakes. Maybe we made a mistake in the derivation and we made a mistake in the power rule and they just happen to be equal. Unlikely, but maybe. We can use GC to always check our results with these. So what can we do? What do we find the rate of change function was for? So we can do R What did we find that the rate of change function was? What was it? You were saying it. Go ahead. What was it? Yeah. Red shirt and glasses. Yes, you were mouthing it. Tell me. Yeah, what's your name? John. What is the rate of change function for square root of x?
Oh, the rate of change function?
Yeah.
Was f of x plus h by f of x over a.
That's absolutely true. So let's do that. That's great. Okay, and let's call the square root function g. Just so we remember what we're doing here. So option B. Okay. And so, oops, forgot to divide by h. Okay, and so what did we just find the rate of change of g is? What did we just find the rate of change of g is? That we want to test. So actually, let's just stick with f here. Everything's f, okay? So f, and what did we find? So we're going to graph the rate of change of, what we find the rate of change of f was, of square root of x.
1/2 x to the negative 1.
Right, 1 divided by 2 square root of x. Okay, so this is what we got. So the blue graph, this is what we got using algebra, right? This is what we got using algebra. How can we test it to see if it's right? How can we test it to see if it's right? I've set it all up for you. Yeah.
You can use the form
Okay,
when h is really, really small.
good. So what should I do?
Y
Y equals,
r.
right, so if f is square root of x, okay, I'm going to graph this one, because this one we know for sure is right? Given that f of x is square root of x, this we trust. And so if I graph this one, I'm going to graph r sub f. You don't use it, when you do this, you don't have to use the subscript. You can just call it anything you want. Just call this function g or something, or whatever to make it easier. Okay, and so what should happen? Okay, so what right now, h, what does GC think h is? 1. Is that small? No. So if we want to check to see that this 1 over square root of 2x, 1 over 2 square root of x is correct, yeah, we need to compare it to the trusted form when h is small. So let's say h is, how about that? So now, let's turn off, we'll just graph the one we found by algebra, right? We did 1 over 2 square root of x. And now when I turn on this one, if we see the exact same thing, then we know we've done the algebra right and we've derived this rule correctly. So because it disappeared, so now it's red plus blue is blackish indigo something. So there's the red one by itself. There's both. There's the blue one by itself, showing that they are the same. They're the same. And we did the math right. So this is what you want to do. And so as you're going to be doing lots of these. You might have discovered the list of 150 of these, which will, over the next week, we're going to eventually be doing all of them. And sometimes you're going to not be sure about what you did algebraically, because it's going to get more complicated in terms of the mechanical things we have to do. You can use GC. You can just set up one GC file that starts like this, okay? That has your rate of change of the function you're going to check, the trusted form, small value of h, and then here you're going to put in the function that you had to take the derivative of, and then here you're going to put in the rate of change, and here you're going to put in what you got when you did the algebra, and then if those two agree, you got the right, you did the algebra correctly. Okay, so use GC by comparing graphs to see that you've check your answers. Check your answers. Like we just did. Okay, questions on that? And like I said, you could just set this general template up, save the file as you would, so like rate of change check or something like that. And then you'll have that file, and then you can just keep changing F and your answer and comparing the graphs.
Did you start the recording?
What's that?
Did you start the recording?
Yes, I did. Thank you. All right, so, let's talk about exponential functions. We're not going to take the time to, well, let's do the first step. So now I want to know what the rate of change of an exponential function is. That's when your independent variable is in the exponent. That's called an exponential function. So first of all, what would the first step be to figuring out a shortcut rule for a rate of change of an exponential function? What would the first step be? Everyone write it down. Everyone do it. Okay, is Nolan here? Nolan, not here. Where's Cassidy? Slater? Cassidy? Not here. Noted. Where's Hector? Munoz? Hector? Not here. Where's Joshua T? Tukunga? Yes, sir. How'd you do? What's the first step in figuring out a shortcut rule for this rate of change?
R sub F of X equals F of X plus H minus F of X over H.
Okay, and then what would it be in this case? Good. That's good. And so then what would it be in this case?
B to the X plus H minus E to the X over H.
Right. Right. Okay, so that's just the answer. So let's write that stuff down. I thought that stuff was there. So he said, we're going to start with this. Hey, they laughed when I just put the answer up there. We're making progress, right? This is good. Okay. All right, and so then for this particular one, it's going to be, he said, b to the x plus h minus b to the x all over h. Okay, so this particular, so we've derived a lot of these, okay? We're not going to do that, we're not going to take the time to do this one. When you do the math and do the analysis, here's what you get. The rate of change of an exponential function is, it's actually, you start off with the rule itself. You start off with the exponential function, and then it's actually a constant multiple of the accumulation itself. So this is a key fact. If you have an exponential function, its rate of change is a constant multiple of the accumulation itself, and that constant multiple is the natural log of b. So that's very noteworthy, right? These are very special functions. When the growth or the decay or the covariation is exponential, the rate of change is actually just a constant multiple of the original accumulation function b to the x. So when is the natural log of b equal to 1? That's a very special case. When is natural log of b equal to 1? When b is? This number e. Number e is like the number pi. It's this special constant. And that's 2.78182846, right? And it goes on and on. Just like pi, it's an irrational number, infinite, non-repeating decimal. That's the value of b for which k equals 1. So this is a very, very special function when you have e to the x. Because what? Its rate of change value at any moment is the same as the value of the amount, of the accumulation at that moment. Very, very special. So we've got exponential functions are always natural log of the base times the original function. That's the rate of change. But when that base is e, that coefficient natural log of b is 1, and so you end up, the rate of change ends up being the same as the accumulation, or the amount, at every moment x, at every moment x. So super special function in terms of that the rate that it's changing is same as the amount that you have. That's really, really special, right? Okay, and just a note, make sure you don't say that the rate of change of one of these, like b to the x, is x b to the x minus 1. Know where your independent variable is. If it's in the base, then you use the power rule. If your x is in the base, that's the power rule. If your x is in the exponent, that's exponential. Totally different rule, right? So know what you're doing, right? Know that when the x is in the base, that's the power rule. Okay? When the x is in the exponent, that is the exponential rule, natural log of 11. So somehow organize your brain to distinguish between those so that you recognize what you're working with at any given time. Okay, questions on that? Again, we didn't derive these because we've deriven a lot of other ones. I believe the derivation's in the book. If not, happy to have a conversation in office hours to explain how we get this rate of change function from this, right? So it all starts here. This is where it comes from. But we didn't connect the dots from here to here. All right. So if you want to connect the dots from here to here, I believe it's in the book, but I would be happy to tell you that or show you that. Okay. So let's summarize. We've got all these now. We've got a constant function. We've got a constant times a function. We have the power rule. But we've seen that the power rule is not just for, it's hiding. It's hiding. My pen is, it's hidden from there. It's in the shadow. Okay, so this is saying that it's only good for counting numbers, but we've seen that it works for n negative and fractions, right? So it works for any value of n, okay? We got the sum rule, and now we got the square root. Square root is 1 over 2 square root of x, or 1/2 x to the minus 1/2. We've got exponential, which is ln of b times b of x. And then a special case of that, the special case where your natural log of b is 1, is e to the x. And that rate of change is e to the x. So we're racking up our rules here. Remember, the more rate of change functions we can find in closed form allows us to find more and more open form accumulation functions and write them in closed form, right? Those integrals, right? So the more of these closed form rate of change functions we know, the more of these integral open form accumulation functions that we can write in closed form using the fundamental theorem. Okay? And we'll revisit some more of that on Wednesday. Any questions on any of the rules? Okay, so let's talk about, let's do this, practice. Let's try this one. Here's P of X. And remember, so we always want to identify overall structure of things because that determines or governs the direction we go. Okay? So we're going to identify the structure first. Of all those rules that I just listed, which one of those rules matches up with the structure of this function P? Of all those rules that I listed, which one of those rules matches with the structure of P? Okay.
Sum and difference rule?
He wants sum and difference rule. Agree? Yep. So sum and difference rule means that we attack these one at a time. We do the rate of change of each one. So we come to this one first. And we look at this. Right there. That's the first term. What's its structure? What's its structure? Constant times a function. Constant multiple. And we know in that case, constant makes it 0, right?
No.
Okay, so lots of students have fallen into that trap. If it's a constant times a function, you hold on to the constant, right? You hold on to the constant times the rate of change of the function, right? So you hold on to the constant times the rate of change of that function, which is what? What's that structure? What's the structure of that? Sum again, right? So we have rules within rules within rules, right? And so to figure out what rule we're using, you got to look at the structure of what you have. Okay. Next one. What rule applies? Think of this as x to the first. Power rule, right? Minus 2e to the x. That's just our e to the x rule. Another power rule. Square root. E squared. Which rule is that? Power rule, right? No, that's just a number. There's no x in it. That's just a number. So we're subtracting a constant. Okay, go. Find the rate of change of p. Okay, where is Gabriel? Yeah, Juarez?
Yeah.
All right, how about this first part? 4 times quantity a to the x plus x to the minus 8. How's you doing that?
Take the 4, leave it.
Leave it. Good.
Times, parentheses, 8 to the x, times the natural log of 8,
Good. Applying the exponential rule.
minus 8x, the negative
Okay, how did you do on that first part? Nailed it, right? Nailed it. Okay, so use the constant multiple rule, use the exponential rule correctly, use the power rule correctly. Where is Mark Valdez? Mark. There he is. How about these next couple? Did you get what's the rate of change of x?
Is it from the square root of x?
Nope. So if we think of it as x to the 1, apply the power rule. What would it be?
It's the same.
Okay, so it'd be 1. So you bring the coefficient down in front, and then what do we do to the power?
It'd be 0 because it's a constant.
Right, so then what would we get in the end? 1 times x to the 0 is the same as what? 1. 1. Yeah, so we just get 1. What about minus 2 e to the x? Mark. Okay. Where's Tynan? Shifit. Tynan? Eden. Eden God. Okay. Fatma, Rahi. Yeah. Did you get the next one? What is it? Minus, so what is it? This is actually constant multiple rule. So minus 2 e to the x. How about that? Do you want to do the next one too? Go ahead. 10.7 x to the power of 9.7. And then minus what? 0, right? Constant. We talked about that. E squared is constant, so we're done. There it is. Questions on that example? So I think that one incorporated most of the rules that we've learned so far. Any questions? Yeah, Aiden? If you want. It doesn't really make it any simpler or not, so optional. You can leave it like that or distribute it. Yeah, Jacob. Well, I was kind of helping him through that. Because he didn't know what that was. But yes, it's just 1. Yeah. Other questions? Yes, sir.
For the 2 e to the x,
Yeah.
once you get the e to the x, probably with e to the x times log of e.
Yeah, but remember, this is the very special case, right? What is natural log of e? Yeah. Yeah, remember e to the x, rate of change is e to the x. So we don't need to write down the natural log of e. So this is this very special function where the rate of change is the same as the amount for every moment. And we could write down ln of e, but it's redundant. It's not unneeded. Okay? Other questions? Okay, so what about a composite function? A composite function. Composite function is where you have one function, the dependent variable of one function becomes the independent variable of a second function. Okay? So the independent the dependent variable of f, so we take what comes out of f and that becomes what goes into g, and so it's like a two-step process, right? A two-step process where the dependent of one becomes the independent of the next. So it's like we're running this initial value x through 2 processes and getting what the end result is. So for instance, we could write m as f would be what? X cubed minus 5. And then g would be what? So we're taking the dependent of f, what comes out of f, and putting it into g to get m. And what would g be then? Square root of x. See that? And so then for this one, the first process on x is? Yes, there's actually different ways to do this, but one possibility would be 3x to the 8, and then we take the result of that and process it through what function? E to the x. Similarly here, first f goes through the process of 1 over x squared. We take that result and put it in the process sign. So all of these m, p, and q are what we call composite functions. There's actually there's a two-step process going on with the original x to get the final value of the dependent. Okay, so all these are composite functions, and we haven't seen a rate of change of these yet. So let's look at that first one. So we see its square root. So here's a couple possibilities. Is it 1 over 2 times the square root of that inside part? That kind of fits the square root rule, right? Or maybe it's the square root rule, and then we also do what? The power rule inside. So here's some, maybe based on the rules that we know, here's some possibilities. How can we see if they're right? GC, right? So let's use the trusted form on M to get the actual rate of change function, and then let's graph these two possibilities and see if they're right. So we've got the trusted form, and we're looking at, now f is what? Square root of? Is it x cubed minus 5? Is that right? Was that what m was? Yeah, okay. So what was the first? So we're going to graph that. We'll graph it red. So what? I'm graphing the trusted form now. I'm graphing r sub f, which is in the form f of x plus h minus f of x over h for a small h. So we know this is correct. We know for sure that is the rate of change function for that function we called m before. So what was the first possibility? We said, let's apply the square root rule and leave that inside as it is. So if I graph that in blue, if they don't match up, that conjecture is wrong. And they don't. What was the other thing? Maybe we apply the square root rule, but then we take the rate of change of the inside. Maybe we do that. So 1 over 2, then 3x squared. Was that the other guess? And if they don't match, it's wrong. So it's something else. So those were good attempts based on the rules that we know, but it's something else. So here, GC doing some work for us. These conjectures for the rate of change of m based on our square root and our power rule, neither of those are right. So we're going to kind of figure out what this is. What is this? And you read about it. So let's work through this. So suppose that a function f has a rate of change with a function r sub f, and suppose we have this fact here. At the moment 6.1, the rate of change is 3.8. What does that number 3.8 mean? We've been asking it all semester. Given a small change in x around 6.1, what do we say then? Yeah. Started saying, yeah, please. Excellent. Excellent. So for a small change in x in the vicinity of 6.1, the change in y, or the change in f, would be 3.8 times as much as that change in x, that tiny change in x. So we could write it this way. We could say that the change in y is about 3.8 dx, or about r sub f at 6.1 times dx. This is this meaning for rate of change, right? Change in y equals m change in x. So if we have a composite function, all right, so I'm going to go on. We need to move a little bit. You can check the video if you want to finish your notes. It'll all be on the video. So suppose we have two functions. The rate of change of f is 5. The rate of change of g is 3. And we're interested in g, the rate of change of g of f of x. Okay? So here's where we're interested in the rate of change of g of f of x, like we were talking about. The rate of change of f is 5. The rate of change of g is 3. So what does this mean? It means that if we let x change a little bit, what's going to change first? Looking at g of f of x. If we let x change a little bit, f is going to change. And how much is f going to change? 5 times that small change in x, because the rate of change of f is 5, right? So if x changes a little bit, f is going to change 5 times as much. Okay? But when f changes that much, how much is g going to change? 3 times that much. This is key, right? So now we have a little change in f. that came from the change in x. And now g is going to change 3 times that much. There's our change of 5. So the rate of change, so g is going to change 3 times as much as f changed. So really what we want to know is, given that little change in x, how much did our composite function change? By how much did our composite function change when we had that little change in x? 15 times as much, right? This is the key to, so when we change g of f a little bit, the output of the whole function g of f of x changed 5 times 3 times as much. Where did the 5 come from? That was the rate of change of f with respect to x. Where did the 3 come from? That was the rate of change of g with respect to f. So if x goes through this process, then in the rate of change, it's going to go through that dual process. That x is going to go through, first it's going to give us whatever f is going to change, in this case by 5. And then if f changes by 5, then g is going to change by 3 times as much as that. So then the whole amount, the whole multiplier on the change in x becomes 15. So this is our m. This is the rate of change of g of f of x with respect to x. It's a product of the rate you get in the first process times the rate you get in the second process if that first one changed that much. Okay, so let's summarize that. So if f and g are functions having rate of change functions rf and rg, then the composition is this. The change in f is r sub f x times as much as the change in x. And then the change in g then is r sub g times as much as that change in f, not x. So this is a key part to this. The rate of change of g now applies to the change that we got in f, not x. So the rate of change of g, the composite with respect to x, is the rate of change of f with respect to x times the rate of change of g with respect to f, as in Frank. Okay, multiplication is commutative. So when we use this rule, we often use it in the reverse. We do the second one first. When we use the rule, we often do the second one first. But conceptually, this comes first. Just remember that. You change x a little bit, the first thing that happens is f changes by some amount, and then g changes according to the change in f. So although we apply it in this order, remember that it's really origination comes in the opposite order. R sub f of x first, and then r sub g of f second. Okay, so let's go back to our function m and apply this now. So we had f was x cubed minus 5, and g was square root of x, right? So to start here, we'll do it in the order of the idea. So first, if x changes a little bit, then f changes how many times as much as that change in x? 3x squared. Okay? And then if f changes by 3x squared, how much does g change by? What multiplier? So it's going to be what? 1 over 2 times. But so this was where we said it's how much g changes with respect to f changing, not x. So we're gonna leave the function f in there. So it's the rate of change of f with respect to x and the rate of change of g with respect to f. With respect to f. So we leave that interior f as it is. So the two things we attempted, first we tried just this, and then we tried this with that plugged in. But so you see that this is neither of those. So we'll use GC, and we'll confirm this. So this is applying that rule that we found, that this is what? The rate of change of the interior with respect to x, and the rate of change of the exterior, g, with respect to f. Meaning leave that interior function as it is, x cubed minus 5. You don't put 3x squared in there. You leave that interior function as it is. All right, let's check our trusted form here. So we'll go back to GC. And now we're going to try what we just found, which was 3x squared times 1 divided by square root of 2, square root of, and we want indigo, right? Indigo, here we go. Indigo. So there's just the trusted form. There's both. There's just the algebraic form. They're the same. So I want you to do these other two examples. So this was 3x squared, square root of x. Oh, sorry, x cubed. So here's what we're doing. We're doing the rate of change of f times the rate of change of g with respect to f, meaning leave f as it is when you do the rate of change of g. And so the language we're going to be using is, we call f the interior function. Sorry. And then g is the exterior function. I think it helps to use that language. Exterior and interior. So here what we're doing. We're doing the rate of change of the interior, f, with respect to x, times the rate of change of the exterior, or the whole thing, but with respect to f. So where's David Samuels? David. Yes, sir. Did you do the second one? Sure.
So the first one would be 4x.
Good. So the second part would be the rate of change of this thing with respect to leaving f as it is. So what is the rate of change of e to the something? It's just e to that something. And we're leaving that interior as it is. That's g with respect to f. Rate of change of g with respect to f. How can we rewrite 1 over x squared? That way we can do the power rule. So we want to change that to x to minus 2 so we can do the power rule. So how about this last one? Where is Christian? Still missing. Where's Jaslyn? Buenafor. Can you do this last one? Good. Oh, we never did that. So the rate of change of sine x is cosine x. So be cosine of f as it is. Rate of change of sine is cosine. Okay, you got written homework for Wednesday?